I think I'll start with the fact that this is week 8 and they're only this week and next week to go. And we have a fair amount to cover, but we're pretty much on schedule, so I'm not too concerned. This is the second half of section 4.3. And essentially it's just continuation of where we left off. So we know how to find when a function is increasing and when it's decreasing. It's all about the first derivative being positive and negative. We can also find the coordinates and local max and min and all that good stuff for using, again, the first derivative. What we're going to add to it is, and we've talked about it before, right? Happy face, sad face. We're going to look at concave up and concave down and points of inflection. And then at the end, you put the whole thing together and you check all your things work by graphing it in Desmos. And there are 6 basic families of functions. I'll hopefully get through most of them today. And whatever ones we don't, you'll just fill in on your own time. Where we're going to find all of these things. Because technically you can't really find concavity because it uses the second derivative until you've found the first derivative anyway. So in some of these questions, I'm going to go through the whole set, and then others, we're just going to bypass the increase and decrease and move straight on to the concavity. So that's kind of the goal today. Seeing if I can, hold on a minute, if I can find a question. There we go. So we're going to start with the polynomial, and it's always a good idea to pick theirs. Otherwise, you make your life hard. So here is an example from question 2. And so it's going to be 540x plus 3x squared, take away 2x cubed. And this one, we're going to go through the whole thing. We're going to do all of these things. So first thing I'm going to do is find the first derivative, which is pretty straightforward. Then I'm going to pull out a common factor of 6. And that I'm not going, I should be able to do that. And we got that. Now I need to solve when is the derivative 0. There are no places where that derivative is undefined. So that means I'm going to have to solve. Very often that's the point where people have the most difficulty, because you really have to do, some kind of algebra factoring or whatever, and that can be a challenge in some cases. Right, so I'm trying to find out what makes this 0. And if I divide everybody by 6, I get that. Now, normally quadratics aren't a problem, except when the quadratic looks like this, because we don't really factor quadratics when they're negative here. So what I'm going to do is essentially multiply everybody by -1, and then I can rearrange the order. Or I could move everybody over here and get the same effect. Now this quadratic is factorable. And I know it's got an x and an x because that's an x squared. Since this number is -90, I know that's a plus and a minus. So it's all a matter of figuring out which one works. Has anybody got a combination of -90 that works? Because there will be one and it's unique.
Nine, 10.
And this generates a critical number. It's essentially what we call these orders of x. And this one generates a critical number. So what we're now going to do is find out when the function is increasing and decreasing, and local max and mins while we're at it. So I draw a number line. I need to be at least -9, so I'm going to have a -10 here. A -9, 8, 7, 6, 5, 4, 3, 2, 1. There's a 0. 8, 7, probably put a 5 in and go 1. There's a 5. There's a 10. One more for luck. So we need a number line that contains these two numbers. And at x equals -9, I put a little dot and I put a little 0 to remind me that the derivative is 0 at that point. And then way over here, another 0. And what I do now is I pick some test points. So if you imagine the places where the critical numbers are, what that essentially does is it breaks the number line into 3 main areas. And so I'm going to have to choose a test point in this region, one in this big region in the middle, and lastly one at the end. On this side, I'm going to choose -10. On this side, I'm going to choose 11. Anybody want to tell me what I'm going to pick in the middle?
0.
I always, I like 0. I always pick 0 if it's a choice. And, I pick numbers like 1 and 2 if they're a choice as well, make my life easy. Now, for each one of those fellas, we need to find out what the derivative is at -10, what the derivative is at 0, and what the derivative is at 11. But it's not a good idea to do this thing because I've distorted it so much. I really need to go back up here. And I don't even care what the number is. I just need to care if it's positive or negative. So I'm going to try this in my head. That's 90, that's 80, take away 100. That's going to be negative. 0 is pretty easy. It's going to be positive. 11 is going to be negative. Or you can do it the long way, and that's fine. So what do we have? We have negative in this region. Because this is positive, everything in this region has to be positive. And right at the end, we have a negative. So I can now answer when the function is increasing. It's increasing when the derivative is positive. So that's going to be any value from x is -9 all the way up to x being equal to 10, curved brackets. And it's going to be decreasing when the derivative is negative, which means here it's going to be decreasing, and here it's going to be decreasing. And that's two separate regions, so anything less than -9, union anything bigger than 10. Are we comfortable with that? That this table of signs allows us to find increasing and decreasing intervals. Then we're going to do local max and local min. Right. Here the derivative is negative. That means the curve's going down the way. Then it's 0, and then it's positive. That means we have a local minimum at x equals -9. Over here, on this side, the derivative is positive, so it's going up. Then it's 0, and then later on it's negative. That's a local max. And that local maximum is happening at x equals 10. But very often, the homework says they want to know the value of the local minimum and the value of local max. And when you see the word value, what they're really saying is, what's the value of the function? What's its y coordinate? So you go back to the original and you find the value of the function at 9, and then you find, and I said 9, that's negative 9. The value of the function at negative 9 and the value at 10. That's why we were given calculators. So at negative 9, the original function then is 540 times 9 plus, let's try that again, times negative 9 plus 3 times negative 9 squared. Take away 2 times negative 9 all cubed, and I get the ridiculously big answer of negative 3159. If I plug in 10 here, what do I get? I get 5,400, add another 300, take away 2,000. And this fella here ends up being plus 3,700. So these are long questions, as you can see, right? And we're halfway through just. So we've differentiated, we found out when the derivative is 0, we drew our number line, we put in the x coordinates, so the places where it's 0, they're called critical numbers. We chose 3 test points to get this bit. That allowed us to find intervals of increasing, decreasing, and the value of local max and the value of local min. Now we're moving on to the next bunch. First thing I'm going to do is rewrite the first derivative. And that's this guy here. I don't want it factored. I don't want it altered really in any way, like the pure untouched first derivative. Now we're going to look at concavity, and you get concavity from second derivatives. So that's 6 take away 12x. You comfortable with that? Now, we want to solve when is the second derivative of 0. So it's virtually the same kind of stuff, only this time a lot less work. Can I just do that in my head and say x equals a half and you're happy where I got it from? You could subtract 6 from both sides and divide both sides by negative 12, but you're still going to get a half. So we now just do our number line again. The difference is that this number line is going to contain information about the second derivative. So how about -2, -1, 0, 1, 2, put in little half marks. Right there, at x equals a half, the second derivative is 0. And I don't need to worry about undefined because that function is never undefined. And I do, just like before, I do some test points. And the test points are going to be, I think, 0 and 1, because I have no imagination. And we find the value of the second derivative at 0 and the value of the second derivative at 1. If you plug in 0 here, the answer is positive 6. And if you plug in 1 here, the answer is negative 6. So I know here, oops, got all my different colors going, it's positive, and that makes everybody in this region positive. And on this side, it's negative, so everybody is negative. Now that looks almost identical in the sense that it's created the same way, right? That was the first derivative, and you see the second derivative, right? The same processes, essentially the same thing. We just interpret this differently. That doesn't mean the function's increasing, and that doesn't mean that the function is decreasing. What it means instead is that it's concave up, right? It looks like a happy face, and it's concave up from -infinity all the way up to half, and it's concave down all the way from 1/2 to infinity. So pluses mean concave up, negatives mean concave down. And to finish with this, we have a point of inflection. Now, the point of inflection happens when there's a change from a concave up to a concave down. See, if this had said positive, 0, positive, that wouldn't be a point of inflection, right? It has to be positive, 0, negative, or negative, 0, positive, right? It has to be a changeover. And the point of inflection here is at x equals 0, but what they want to know is the coordinates of the point of inflection. So if you take 0, and since you're after the coordinates, you're away back here, oh, let's see, it calculate 0, 0. So we've now found everything you could possibly want to know, and probably some more, on this particular polynomial. I know when it's increasing, I know when it's decreasing, I know where its local max and mins are, I know when it's concave up, I know when it's concave down, I even know where the change from happy to sad face happens. It happens at the origin. So the last piece of this puzzle is you check it by drawing it. So Desmos is going to take that. I know just by looking at the numbers that I've got that the scale is going to be a little bit hard, but we'll figure it out. Has anybody, can you see Desmos right now? Am I on the right screen? Okay, so I'm putting in really ugly numbers, so don't be surprised if the picture looks nothing like what we think it should do. So it's a 540 plus a 6x, take away a 6x squared. Right, you see that doesn't look anything like our graph. That's just because the vertical scales are so bad. Now I am going to go over here and I'm going to change the x coordinates. Actually, I don't mind the x coordinates. Negative 10 to 10 basically has everything I want. But I know that the value of this guy is some ridiculous number like 3,159. So I'm going to make it 3,200. And this guy on the other side, it was, I think I got 3,700. So let's put 3,800. Oh, I didn't do my windows wide enough. I'm saying negative 10 to 10, but that really isn't a good idea. How about negative 20? To 20. Okay. Did I get that wrong? Oh, darn it. Oh, there's my mistake. I just wrote in the derivative. I apologize. I can probably keep the window. I was looking at the wrong graph. This is the original function. There we go. And 540 with an X on it. There we go. Oh God, that looked harder than it was. Now, let's see if we've got all the features. Can you see that guy there? Doesn't he kind of match the local min? That guy there's the local max. Can you see the concave up and the concave down? Can you see the transition point at the origin? Pretty much everything that we did, isn't it matching exactly what the graph said it should be? Now, if I take this x out, wouldn't that not look like the information that the derivative told me? So can I use it as a check? Where's the local min, right? Where's the local max, right? Not really where they should be. Any questions about that? Because as you can see, it takes a long time to do.
How did you decide that the point of inflection was x equals 0?
Oh, that's where the second derivative was equal to 0. So the second derivative was equal to 0. There's my page. Oh, darn it and spice. It's not 0, isn't it? It's a half.
Oh, okay, cool.
You'll have
Okay.
to figure out what the Y value is.
That's
I
fine.
think I was just scanning. I saw that instead of that. I've already mentioned to you my scanning issues. Right, let's move on quick. That's a lot of stuff on one question. But the good news is that really once you've done one of these, haven't you done all of them? Because it's going to be the same process, just with different functions. So that's me done a polynomial. I'll get you a couple of examples. Question 3. I'm only going to do the second derivative part, right? The concave up, concave down part. So we have a function, and it's x, the square root of 6 take away x. And in this question, there's going to be an extra little bit at the beginning. It's always a good idea to check what the domain of your function is, right? The usable values of x, just in case, because it will happen, that you'll get a solution, oh, x equals 12. And then you'll say, but I can't use it, right? Now, in this function here, that doesn't matter. But won't that square root have to be positive? You can only do square roots of positive numbers. And for that to happen, won't x have to be 6, right, or less? So that means negative infinity to 6 is my domain. Are you okay with that? That 6 take away x must be positive. That means x has to be less than 6. Right. Now, let's move on to the calculus. I'm going to write it like that. To differentiate this function, I have to recognize that it's really two things multiplied, and so I'm dealing with a product rule, f dash j plus f of j dashed. If you differentiate this guy, you get 1. You leave that guy alone. You leave the first guy alone, and you differentiate this, you get 1/2 6 minus x to the negative 1/2 and times the inside function, which gets you another negative 1. So we have this guy. And this guy. Okay, I'm going to pause for a second. Pretty ugly answer. I need to make it look pretty.
Factor the 6 minus x to the negative 1/2.
Is it getting a little bit more obvious once you've seen about 4 or 5 of these weird negative power common factors? Right now, if you take it out of here, you're going to get negative 1/2 x. If you take it out of here, you're going to get 6 take away x to the power of 1, because 1/2 power take away another negative 1/2 gets you 1. And so this fella here, I'm going to write him down at the bottom. And this guy is 6 take away x, take away that one, becomes 6 take away 3/2x. And to complete the style points, make it look like the original. Now, I would be looking for critical numbers. That's places where the derivative is 0, which is the guy in the top. What would that look like? 12. 3/2, 12, 4. Yeah, x equals 4. And I'd be looking for when is it undefined, which would be x equals 6. So that would be what we're doing. But I'm skipping by that. We're going right on to concavity, which means I need to differentiate this again. And for differentiation purposes, I have to turn it back into that guy. You recognize that this is a quotient rule, an f over g. So we're going to have to do an f dash g, take away an f g dashed all over g squared. If you differentiate the top, you get -3/2. Leave the other guy alone, you get that one. Take away, leave the first thing alone, and differentiate the bottom. And that's going to get me 1/2 6 minus x to the -1/2 times the derivative of the inverse inside function, which gets me a -1. And the whole thing is squared on the bottom. Actually, that's not too bad, because if you square a half power, you get that. So my second derivative is -3/2 6 minus x to the half. Take away, or two takeaways make it an add. 1/2 6 take away 3/2x, 6 minus x to the -1/2 all over 6 minus x. I don't have a problem with the bottom, so I'm just going to write 6 minus x again. But I should be able to factor the top, agreed? Okay, what common factor can you pull out of the top, the numerator?
6 minus x to the -1/2.
Is there a kind of deja vu thing happening here that you end up doing the same kind of thing more than once? So I could pull out halves and things, and actually could probably pull out other combinations, but I'm not going to. We'll do that later. Right, if you pull it out of here, you're left with 1/2 6 take away 3/2x. And if you pull it out of here, you get -3/2 6 minus x to the 1. That guy is going to come downstairs, and now you have an extra half power, so you have 3/2. This I'm going to multiply through, so that's -9. Take away 2 negatives, make it a plus, so plus 3/2x. And that's going to be plus a 3. Take away a 3/4 x. And that's going to get me -6 plus 3/4 x over 6 minus x to 3/2. Don't need this next line, but it's going to bug me, so I'm going to do it. It just looks nice in my brain that way around. And this fella here is 6 minus x cubed. Actually, that's fine, but this is, in my opinion, a little bit nicer. So after a lot of calculus, get much calculus and algebra, we finally got to the best version of the second derivative we can find. And now we are going to find, essentially, its critical numbers. So we're going to solve when is it 0. And in this case, we're also going to solve when is it undefined. Okay, if you look at this fraction, is there any value of x that you could plug in there that's going to make life hard to calculate? That's typically what undefined is, right? So there is a value of x. What value of x is going to make this a problem?
0. Sorry, 6. It makes it 0.
The thing that makes it 0. You're right, 6. Now, on the top there, if you want the derivative to be 0, don't you only focus on the top being 0, right? And if you want the derivative to be undefined, don't you only focus on the bottom being 0, right? So they're different parts of the fraction. Right, top. I need to solve that. If I add 6 to both sides, I need to solve that. If I multiply both by 4 and then divide by 3, I get x equals 8. You want to trust me in x equals 8? Right. Now, something very strange has happened. This derivative, this second derivative, is only going to be 0 when x equals 8. Is 8 in my domain? So this is not usable. In other words, ignore it. Which means that this curve only has an issue at x equals 6, but isn't x equals 6 at the extreme end of this function? Right, there isn't anything to the right of it. 6, right? It's 6 or less. What does that do when I do my little table thing? It's going to look kind of boring. At this point here, it's undefined. I'm talking about the second derivative. So all I need to do is choose a test point in this region. And pick any number I like. Let's pick 3. And when I pick 3, the answer is positive. And now I want to interpret that. Well, this means that this shape is concave up for values of x from -infinity to 6. In other words, for the entire graph. And it has no point of inflection. And it's never concave down. That's a kind of weird looking function, agreed? I'm seeing if I can get x Desmos up. Let's check it out with Desmos. This time I'll make sure I write the correct function. Y equals x. I think you can do SQRT. Yeah, square root of 6. Take away x. And that is definitely a horrible scale. So I'm going to change this guy to, no, -3.
Oh, we can't see Desmos.
Oh, you can't. Thank you. Can you see it now?
Yes.
Yeah. The window's horrible. So I'm going to change this number to -3. Hopefully that's enough. I'm going to change this number to +3. And that is enough. Right. I need a lot less x's, I think, as well. So how about x is -5? Oh, no, 5 is a bad choice. -10. And 10. So you sometimes have to play about with windows to get the shape. Right. Okay. Now, there we go. Would you agree that this shape has, although we never bothered to find it, a local maximum at that guy there? Right. Would you agree this shape is not changing? Isn't it one big concave down? Concave down? Well, I got my sign wrong. That's fine. I fixed my answer. But it's definitely correct. It's concave, whatever it is, every way. That's cool. Okay, I got my signs wrong, but that's because I did it in my head instead of doing it in a calculator, which is always a good idea to do things on your calculator when I'm involved. We've done polynomials and we have done radicals. We should do a trig one next, I think. What does that look like? So an example, oh, by the way, that question I just did is version 3, or a version of question 3. So the trig one is version of question 5. And we're only going to do the concave up, concave down part. And this one is a little bit different because we're only going to be interested in answers that are in the range 0 to 2 pi. So if you get an answer that's 4 pi or negative pi, you don't use them, right? So first derivative, well, if you differentiate a cosine, you get a negative sign. That says cos squared theta. If you think of cos squared as being cosine theta squared, might make it a little bit more obvious that it's a general. So it's 2 times the cosine of theta to the power of 1, followed by the derivative of the inside function, which is that guy. So that is negative sine theta. So I have negative 2 sine theta minus 2 sine theta cosine theta. Now, if I wanted to know where all the local max and mins and increasing and decreasing, I would factor that out and solved. But we're only interested in concave up and concave down. So I'm going to do a second derivative. If you differentiate this guy, you get negative 2 cosine theta. If I call the negative the 2 and the sine theta, if I call that entire package f and this little guy here g, then we can do f dash g plus f of g dashed. Otherwise, I keep the negative on its own, put a big bracket around that, and then remember to subtract everything when I'm finished. That also works. So we have negative 2 cosine theta. And if you differentiate this entire package, you get negative 2 cosine theta times cosine theta plus this guy times cosine theta, and the derivative of that is negative sine theta. So I have negative 2 cosine theta, negative 2 cosine squared theta, plus 2 sine squared theta. It's funny how things, coincidences work. My trig class is just finished on Friday doing exactly this kind of problem. We are going to have to solve when is a trig equation, in this case that guy, equal to 0. And we're going to have to solve not a very nice one. Okay, it's a while ago, but hopefully it's fresh enough in some of your minds that if you want to solve a trig equation that has cosines and sines in it, what you need to do is you need to change them so they're all cosines or they're all sines. I think it's much easier to change that guy into a cosine of some kind. So it's going to be negative 2 cosine thetas, negative 2 cos squared thetas, plus 2 lots of sine squared theta rewritten using cosine squared theta. I'll take a volunteer on that. What is sine squared theta equal to in terms of cos squared theta?
Negative sine squared theta plus 1.
And very interesting way of saying it. And it's correct. It's me and my little idiosyncrasies. I like plus takeaway rather than takeaway. Add. So it's that. So I now have negative 2 cosine thetas, negative 2 cos squared thetas, plus a 2, take away 2 cos squared thetas. And if I combine like terms, I have -4 of these guys, take away 2 of these guys, plus 2 equals 0. Now, I do not like quadratics with negative anything squared, negative x squared, or as in this case, -4 squared. So I'm going to multiply everybody, both sides, by -1. The net effect of that is just to change the pluses into minuses and vice versa. Okay, we're going to factor this guy, but is there any number we can take out first as a common factor?
2.
So let's do that. Every little bit helps. And this, again, is a bit of a challenge. Hopefully you're up for it. I want to factor a quadratic in cosine thetas, because that's essentially what that is. It's just like x squared plus x take away 1, right? Mathematically, there's not a lot of difference.
The cosine still has a 2 on it.
This one here?
The first one, cosine
Oh,
squared.
this one, well caught. So 2 cosine thetas, right? What is the combination of ones? Well, you can only have 1 and 1. But one of them needs to be +1, right? And the other needs to be -1. So all I need to do is figure out which is plus and which is minus. And we've kind of done this. So what you got? Which one is +1 and which one is going to be -1?
The left one's gonna be negative.
And to check it, you would FOIL it out. Now, if quadratic equations are things that you're not comfortable with because you haven't really dealt with them a lot, here is the equivalent quadratic. If I went and said to you, can you factor that? I hope a lot of you would say, yeah, I've done worse. And you would be going 2x plus 1 minus 1. Wouldn't you be doing that? Well, that's really no different. Isn't that 2 something squared plus a something minus 1, right? It's the same idea. Okay, solving this fella needs to be equal to 0, which makes this fella -1, which means I am looking for an angle in radians whose cosine is equal to -1. So I am looking for a point, right, an angle that has an x coordinate of -1, and that is pi. And this fella is 2 cosine theta take away 1, and that has to be 0. And so that becomes 2 cosine theta has to be 1, and that becomes cosine theta is a half. So I'm looking for angle or angles where the x coordinate is a half, and the answer I get is pi/3, or at least that's one of them. And the other answer I get is down here, and that's 5/3. So we found 3 critical numbers for this function. So draw my number line. I know I have to start at 0 and finish at 2 pi. They told me that at the beginning. I'm going to put pi in the middle. What kind of angles am I looking for? I'm looking for 1/3 pi. Guess we make that 2/3 pi. Make that 4/3 pi. Make that 5/3 pi. And we have a second derivative equal to 0 at 1/3, at 5/3, and at pi. And since my second derivative is way over here somewhere, Oh, it doesn't matter. I'm just writing this version down. There's so many versions floating around. I got that fella. Take away this guy. Add 2. And I need test points. So there's where the second derivative is 0. There's another place where it's 0. There is the third one. So I'm going to be choosing test points. Is this X or zeros? It's theirs, right? So I'm going to choose 0. I'm going to choose 2/3 pi. I'm going to choose 4/3 pi. And I'm going to choose 2 pi. For each one of these guys, I'm going to find the second derivative. And that's positive, and that's negative, and that's positive, and that's negative. I hope. Oops. Now, we can tell concave up and concave down, and we can even tell points of inflection. Now, these I haven't verified, so you may want to check them by simply just plugging in the values 0, 2/3, 4/3, and 2 pi, and see if you get a plus or minus answer. But if these are correct, which I hope they are, then you're going to have concave up when things are positive. So that's here. Well, actually it finishes there and here. So that's going to be from 0 to 1/3 pi, and then from pi to 5/3 pi. Oops, pi to 5/3 pi. And you're going to have a concave down, and that's going to be from 1/3 pi to pi, and from 5/3 pi to 2 pi. You could argue that that guy and that guy could be curved or square. I'm going for square. Hopefully WebAssign likes that idea. And there are going to be points of inflection at 1/3 pi, at pi, and finally at 5/3 pi. And to get the coordinate, we would be using the original function. So if you plugged a 1/3 pi into that, you get an answer. If you plugged in pi to that, you get an answer. And if you plugged in 5/3 pi. And then if we had time, which we don't, wouldn't we go to Desmos and look at it and say, oh, all the things we've written here and the first derivative match up perfect.